At Virginia Tech, the Department of Psychology is housed within the College of Science. That's because, like other sciences, such as biology, chemistry, and physics, psychology relies on the scientific method to formulate its body of knowledge. In this video, we'll explore the scientific method, especially as it relates to psychology as a domain of inquiry. The scientific process usually begins with a theory. A theory is a well-developed set of ideas that propose an explanation for observed phenomena. Good theories should give comprehensive explanations, be based on scientific evidence, and make predictions about future aspects of the world that can then be tested. For example, one theory of relationship commitment, the investment model, proposes that one's feelings of commitment to one's romantic partner are primarily comprised of three factors: one's current satisfaction level in the relationship, one's prior level of investment in the relationship, and the quality of potential alternatives. All else being equal, the model predicts that people will feel more committed to their relationships when they are relatively satisfied, have a higher level of investment in the relationship, such as being together for a long time or sharing resources such as a house, and when they believe that their current partner is better than any potential alternatives. In turn, one's commitment to the relationship should predict engaging in the kinds of behaviors that will continue to maintain the relationship over time, such as forgiving one's partner and thinking in terms of we rather than me. Theories are repeatedly checked against the world, but they tend to be too complex to be tested all at once. Instead, researchers create hypotheses to test specific aspects of a theory. A hypothesis is a testable prediction about how the world will behave if our idea is correct, and it is often worded as an if-then statement. Let's go back now to our investment model. We might hypothesize, for example, that if couples have a higher level of investment in their relationship, such as owning a home or having kids together, then they will be more likely to be committed to the relationship, and thus more likely to stay together over time. This now leads to a very important step: collecting objective data and comparing it with our hypothesis. For example, we could potentially get a sample of romantic couples and measure them over time to see which couples stay together and which break up. We could also measure things about the relationship, like investment size, and see if that predicts relationship longevity. Based on our investment model theory, we would predict that couples with a higher investment in the relationship should be more likely to stay together over time compared with those with a lower level of investment. Indeed, this is what many such studies testing the investment model have found. However, even though many studies have found evidence consistent with the investment model, notice that this did not necessarily have to be the case. That is, the data could have either been consistent with the predictions from the investment model, or the data could have been inconsistent. In other words, investment size didn't necessarily have to correlate with relationship longevity. And this leads to our last important point. Scientific theories must be what we call falsifiable. In other words, they need to make a testable prediction that could be falsified, could either be consistent or inconsistent with the overall theory. As an example of a theory that's not falsifiable, let's say that your friend has a kind of silly theory that we all live in a simulated computer reality similar to the Matrix movies. You might say, well, I don't see any evidence of that. And your friend might reply, well, of course not. That's not how they programmed it. According to your friend, there's nothing that can prove this theory wrong. Any apparently inconsistent evidence can be easily explained away by saying it was all part of the computer program's design. And that's precisely what makes your friend's silly theory not be falsifiable. There's no evidence that can contradict it. In contrast, the prediction that we made earlier based on the investment model theory was falsifiable. In other words, it was possible to obtain data that would have disconfirmed or falsified the theory. If we would have found no correlation between investment size and relationship longevity, we would have had to reconsider whether the investment model was fully correct. The scientific philosopher Karl Popper called these kinds of falsifiable predictions risky predictions. Risky because they expose the scientist to the potential that he or she could be wrong. For example, Einstein's theory of relativity makes predictions about how light would move around a body of mass as it bent space-time. This was actually able to be tested during the 1919 solar eclipse. Einstein's prediction here was risky because it made a very bold, specific prediction about the exact degree of light deflection that should be observed. If the data were inconsistent with this prediction from Einstein's theory, it would mean that the theory was wrong, at least to some degree. For more information on Karl Popper's thinking about falsifiability, you can check out the short supplemental video in Canvas. The scientific method is an iterative or ongoing process. As specific hypotheses are tested, theories are modified and refined to reflect and incorporate the results of these tests. More data can also sometimes lead to more questions. Many researchers spend their entire career researching and testing just one or two basic ideas. An advantage of using this scientific process to gather evidence and test our ideas is that it relies on empirical evidence. This can be helpful for avoiding biases that might be the result of human intuition. For example, it might not necessarily seem intuitive or patently obvious that we are all on a round, spinning globe that is hurtling through space at 67,000 miles per hour as it revolves around the sun. Yet, based on centuries of empirical evidence, we know this to be true. However, there are a few caveats worth noting. First, scientific theories represent our best approximations based on current evidence. While these theories may be useful in that they allow us to predict how the world will likely behave, every scientific theory is, to some degree, incomplete, and there will always be the possibility that it will at some point need to be updated. For example, Newton's laws about gravity stood the test of time and were consistent with observable evidence for hundreds of years, until Einstein's theory of relativity updated our understanding of gravity and tweaked Newton's formulas slightly. Second, even though the scientific method attempts to be objective, that is, above human subjectivity and biases, it's not completely immune to human fallibility. The scientific method still requires that a person asks a question and investigates it in a particular way. And the method that people use to gather their data, and the way that they interpret that data, and even the kinds of questions they think to ask in the first place, are all potentially subject to human bias. Finally, it's worth noting that not all important questions can be tested scientifically. There are deep philosophical questions that can't be addressed with scientific processes because they don't make testable, falsifiable predictions. This doesn't mean that these questions are any less significant or meaningful. It just means that we can't address them with scientific evidence alone.